Good morning, evening, afternoon. I have no idea when you are watching this. So good hello. Okay. Last week in Algebra 3-4. So we had a shorter week. We went through the 17th to the 20th with our block. We did 17th two things. Looked at inverse variation for a brief moment. I'll look at it even a little longer here. We graphed reciprocal functions. I'll do a few graphs there. Some rational expressions and rational equations. The only way for this to go short is for me to kind of talk more quickly through them. So I will do the problems. I'll do very minimal teaching meanwhile, but I do want to make sure that it makes sense. So let's see how this goes. Okay, first thing is inverse variation. To do this, you also want to know what direct variation looks like. So direct variation is y equals k times x. K is your constant of variation, meaning it's something that is always like your slope in a way, but that number is always being multiplied by x, and that only works if this is proportionally, if this only is set up as some sort of proportion, meaning if this crosses through the origin. Inverse variation is y equals k over x, and as x gets larger, this was something that we saw, as x gets larger, y gets smaller, and that's something that we really want to look at there. K is still your constant of variation. So let's see an example here. For instance, suppose that x and y vary inversely, which means we're looking at y equals k over x. Write a function when x equals 2 and y equals negative 8, and then find y when x equals negative 10. So to find the function, let's substitute negative 8 for y and 2 for x. Multiply both sides by 2, you get k equals negative 16. So your function is just y equals negative 16 over x. So let's find out what y is when x is 10. Then y is going to be negative 16 over 10, and y is negative 8 over 5. So if it helps, 2 points that you know on this graph, I'm just going to write it here and then I'll erase it. 2 points that you know on this graph are 2, negative 8, and 10, negative 8 fifths. Or negative 1.6 if you think about it that way. That's all the variation stuff is. But here's another set of example problems right here. What if we had some table values and we had to determine whether this was direct variation, inverse variation, or neither? And if it was one or the other, we would write the equation for it. For that to be true, check this out. For it to be direct variation, our constant would always be, if I divided both sides by x, our constant of variation is always y over x. Meaning if I take these terms and I do y divided by x each time, am I getting the same constant of variation? If not, then it's not direct variation. Same thing with inverse variation. If I multiply both sides by x, then my constant of variation is x times y. So if I take these values and multiply them together, and if I have the same constant of variation, if I don't have the same constant of variation, then it's not inverse variation. So let's check this out. Let's see if this is direct or inverse. For direct variation, 6 over 3, right, I'm going to do y over x for each of them. 6 over 3 is 2. 8 over 5 is obviously not 2. 10 over 7, etc., etc. We know this is not direct variation. Inverse variation, 6 times 3, right, if your constant variation is x times y, 6 times 3 is 18. 5 times 8 is 40. Same idea. It's also not inverse variation. So this is neither. This is just some other kind of equation. It looks like it's a linear equation, yes, but it does not cross through the origin. And that's a huge part of it that it needs to have. Okay, let's check out the second one. Direct variation is 10 over 4, the same as 8 over 6, and 6 over 8, and 4 over 10. The answer is no. This is not direct variation, therefore. It does not have the same constant of variation. For inverse variation, however, does 10 times 4 equal 6 times 8, and 6 times 8 equal 4 times 10. Once again, no. This is also not direct or inverse variation. Final one, let's check this one and hope that we land on something good. Direct variation does 32 over 4. How do I say that? Does 32 over 4 equals 16 over 8 let's see, 32 over 4 is 8, 16 over 8 is 2. Obviously, this is not the case. 8 over 16 is 1/2, etc. This is not direct variation. Inverse variation does 4 times 32 equals 16 times 8, and 16, 8 times 16 and 4 times 32. 4 times 32 is 128. 16 times 8 is also the same thing. So all of these have the same constant of variation. So this is inverse variation. And one thing that you'll notice about inverse variation is that x and y values kind of swap after some point. Like you can see there, 4 and 32, 32 and 4. So this is inverse variation. The constant of variation is 128, so the model is y equals 128 over x. We won't graph something that severe with 128, but we will be graphing. That's next. Okay, next thing on graphing reciprocal functions. They come in this form, and I mean, don't confuse the a and k and stuff. That's one thing why you don't. That's one reason why you don't want to memorize equations. If you do, then you're starting to say, "Oh, k is this thing," and right. You got to just make sure that you understand the form. H and k are displacement from your origin. They represent asymptotes. And I won't reteach what we're going to do, but I will redo these problems and explain through. A is a reference value. We've been dividing by a down here, and we've been dividing by 1 down here. As we keep expanding through graphing, I want to divide by all factors of a that I can. So we'll do the first problem here. In this problem, looks like there's no h and there's no k to speak of, so your asymptote lies at 0, 0. So if I go ahead, sorry, I'm going to graph an asymptote here. Make my asymptote the same color as my graph. So this one's going to be red. It's going to go down there. And it's going to go across there. I should probably zoom this out a little bit. I made a very big graph. Okay, so for this first problem, what I'm going to do is graph y equals 10 over x. And for x is not the values that I'm going to plug in. But I'm going to plug in, like, when I substitute values, I'm substituting for the denominator. It just happens to be coincidence this has x in it. I'm going to substitute factors of 10, specifically 1 and 10, because when I divide by 1, I know that my number is 10 up. So here's the thing. Everything's in relation to your cross-section, not the origin, but from here. When I go 1 over, this denominator is going to represent how far I go over. When I go 1 over, the y value, the rest that's in there, is how far I'm going to go up. So I'm going to go up 10. When I divide by 10, when I go 10 over 10 is 1. Now, those are just 2 points, and so far I've only required for you to do 2 points. I'm going to ask you to do more, though. I want you to do all factors of 10. 1, 2, 5, and 10. How about 2? When you go 2 over, you'll go 10 over 2, which is 5. You'll go 5 up. When you go 5 over, you'll go 2 up. Okay, so I want you to list any and all factors of 10 that at least get you some integer values. Those will be best for me to ask you to do there. And half arrow and half arrow. Sorry, the drawings will not be great. Now, that's those versions. Now, how about the negative ones? Negative 1, negative 2, negative 5, and negative 10. When you go 1 over, 10 over negative 1 is negative 10. When you go negative 10 over, you're going to go 1 down, 2 over is 5 down, and 5 over is 2 down. Like I said, I'm not going to spend too much time explaining all of it. You're going to see 2 more graphs besides these ones, and hopefully those will help. And I might delete these graphs as I go, so I think I will actually. So there was that graph. That was the first one. The next one will be y equals 7 over x minus 1. Now this time you have an h value of 1. Your domain, if you want to write that, your x value cannot be positive 1, which means that's also where your vertical asymptote lies. So if I place a vertical asymptote right there, horizontal asymptote still at 0. We're going to see in the blue one when it actually shifts. We're going to do everything in relation to that asymptote, to that cross section there. So factors of 1 or 7 are 1 and 7. Now notice, I'm not going to substitute 1 for x because 1 minus 1 is 0. We can't do that. If I substitute 2 for x, 2 minus 1 is 1. 2 is 1 over from here. So that's what I'm saying. When I go 1 over, 7 divided by 1 is 7. When I go 7 over from here, which is really when x equals 8, I'm going to be 1 up because 7 divided by 7 is 1. And I graph this guy, and like I said, I'm not asking you to graph any more for that one because there are no other factors of 7. Now on this side, same thing. When I go 1 over, I'm going to be going 7 down. And when I go 7 over is now at negative 6. I'll be going 1 down. Graph's not too great. But there we go. Another beautiful graph there. And again, for the sake of time, just going to move on. The last one, the blue one. This is a negative 1 right there. And we have a domain that x can't be negative 4. Okay, can't divide by 0 there. Now this 2 is what you will be approaching with your horizontal asymptote. I've explained that a lot. In class I explained it a lot with the exponential chapter as well. So I'm going to avoid talking about that too much. Just make sure that we know that's where our asymptote's going to be at. Okay, everything's going to be in relation to the asymptote. The only differences here are we're talking about a negative 1. I'm actually going to zoom in again. We're talking about a negative 1, and we're using 1, which means we don't get to practice too many good old factors on this one. Factors of 1 are just 1. So with negative 1, when I go 1 over this way, I do negative 1 divided by 1. I'm going to go 1 down. That's one of my points. There aren't really any other points you can hit except just start talking about other points. If I go 2 over, I'm going to be doing 1 divided by 2. Negative 1 divided by 2. So that's negative 1/2. So in this case, I would like you to try hitting some fractions. When I go 3 over, I'm going to go 1/3 down, 1 over 3. When I go 4 over, I'll go 1 over 4 down, etc. If I went 1/2 over, 1 divided by 1/2, negative 1 divided by 1/2 is negative 2. I went 1/3 over, 1 divided by negative 1/3, or negative 1/3 is negative 3. And when I go 1/4 over, etc., etc., you get negative 4. So that's an example of that graph there. Now notice how it went downward instead of upward because we were talking about negative 1. And it's the same on the other side as I flip that guy over right there with my graphs. Now we will focus more on these. Your quiz will highlight at least one of these, but I want to make sure that you at least get some good exposure now and we enrich it later. So that's what that graph looks like there. And that's graphing reciprocal functions. Okay, you're not going to read this whole thing. All this stuff was simplification rules that we did in our Chapter 7a review. I listed all of these. We had to talk about all these. I'm just showing you that when they ask you to simplify a function, these are parts of the things that they ask you to do. I think I got these off the top of my head, but I think that they all are true. Like terms are combined. This includes rational numbers. Okay, so what that means is if you have two fractions, combine them as one. They ask you to simplify it, write it as one fraction. Get polynomials in descending order of degree. So that means if you have 3 minus x, change that to negative x plus 3. And normally we end up factoring out a negative 1 when we do that, etc. Denominators have to be void of 1s and 0s, meaning we cannot divide by 0. This is one of our restrictions. Common multiples with the numerator, that's a big one. We want to factor out any common multiples. Get rid of those leading negatives, like negative x plus 3, I talked about that. And other fractions. So if you have a fraction within a fraction, like this scenario, we want to eliminate that stuff as well. So there are a lot of different things that we're going to end up doing. The ones that I underlined are the only ones we're going to talk about here, as it seems. Okay, let's do some. Simplify each rational expression, state any restrictions on the variable. So in terms of this, notice how we talked about common multiples. You want to factor out anything and get rid of any leading negatives as well. So there's a leading negative. Let's find a way to get rid of that. So let's practice factoring this entire guy as we can. When you divide, you want to multiply by the divisor's reciprocal. So we're going to flip these two guys and we're going to multiply. So this is going to be x plus 3 times 2x minus 1 all over x times x plus 4 times x is now on top all over. I'm going to factor out the negative 1 from there, and I'm going to be left with x plus 3, and I have 2x plus 1. Sorry, handwriting's going to be kind of sloppy on these ones. You can write these as one fraction. I'm just going to write this. I don't know if it's really a property. If you multiply these two things, you can multiply straight across like that and leave it as one fraction. So I'm going to merge this all as one fraction. That perception might help you understand that certain things can cancel now. I can cancel x divided by x. I can do x plus 3 divided by x plus 3, and those are gone because they are common multiples that are shared. Now what's left on top is 2x minus 1. On bottom, you have a negative 1, an x plus 4, and a 2x plus 1. Now that 2x plus 1 cannot cancel with the 2x minus 1 in any sort of way. The last thing that I do want to do is take care of that negative 1. I don't want that multiple in there. I'm going to go ahead and multiply top and bottom by negative 1 over negative 1. All that matters is negative 1's cancel here and I have a negative 1 on top. So this will become positive 1 minus 2x, or negative 2x plus 1. Doesn't matter which way you write it in that case. X plus 4, 2x plus 1. And there's your final answer. Now let's talk about restrictions. Let's write it in red. Anything in the denominator that can't be true. X plus 4 can't equal 0, so x can't equal negative 4. Okay. 2x plus 1 can't equal 0, so 2x can't equal negative 1, so x can't equal negative 1/2. And also, anything that we canceled out is also something that we should be curious about. Notice that at some point we also divided by x plus 3. Even though it canceled out, we're talking about the original guy that we can't make happen. Like in other words, if I substitute negative 3 in the original equation, I would have an issue. Also, x cannot equal 0, as we saw that canceled out. So there are your 4 restrictions. There were a lot of restrictions on that one. Okay, number 2. This one is an adding guy right here, and to add you need common denominators, and for a common denominator you need to seek common multiples. So what I'm looking at here is addition. I can't add across unless I have the same thing on bottom on both. Notice how I have these factored out here. This has a multiple of x minus 3, but it's missing a multiple of x plus 1. So if I multiply top and bottom by x plus 1 over x plus 1, I can start to go to work. On top, I'm now going to have x plus 2 plus, now here's some fancy stuff that we have to do here. We have to multiply, I'm going to do this. This is x squared plus x minus 2 times x plus 1. So in a box here, only because I've been doing this a lot with my Algebra 1-2 class, they're called generic rectangles. We call it box method maybe. We've been multiplying this way, so I'm just going to do that because I'm just used to it now, unfortunately. This is plus x cubed plus 2x squared minus x minus 2. And this is now all over, because it's a common denominator, x plus 1 times x minus 3. Now I can combine like terms, and you'll get x cubed plus 2x squared. Looks like the x's cancel out there. Looks like the 2's cancel out there. And it's all over x plus 1 times x minus 3. We would be done, but there's a common multiple on top of x squared. So that's x squared, and x plus 2 is still within there. This is all over x plus 1 times x minus 3. And that is the simplified form of that guy right there. Restrictions, nothing canceled out, but restrictions, you cannot divide by 0, so x cannot equal negative 1 or 3. Okay. I'm going to erase some stuff over here to work on number 3. Sorry about that. This one's subtraction. Same idea, only again with a common denominator, we need to really work towards saying what are the multiples and factors here. X squared minus 4, I'm just going to rewrite right now. This is x plus 2 times x minus 2. Okay, that already shows you that, oh, look, we share an x minus 2 here. It looks like this is missing a multiple of x plus 2 on it. X plus 2 over x plus 2. Wouldn't it be nice if we had that there? So we multiply this by x plus 2 and x plus 2. Same idea as last time. We need to start distributing this stuff on top here. I'm going to distribute the x with the x and 4. That'll give me x squared plus 4x. So I need to multiply x plus 2 with x squared plus 4x. 4x, x, and 2. That gives me x cubed, 4x squared, 2x squared, and 8x. I told you I'd be going quickly. Sorry about that. So I have x cubed plus 6x squared plus 8x when I combine like terms. Now here's the important part, this minus. This is minus x minus 1. Notice how I just bracketed, or just put that in parentheses. Because I'm subtracting the x and the negative 1. So you can either write it like that, or you can write minus x plus 1. But make sure that that becomes a plus 1, not a minus 1 in the end. This is all over x plus 2 times x minus 2. The only like terms I can combine here are 6x, 8x, and x, so I get 7x and 1. Normally, I'd ask you to try and factor this to see if there's a common multiple of x plus 2 and x minus 2 here. But because you haven't done rational root theorem, and because let's see, I don't think this combines. Let me check negative 2 here really quickly. Negative 8, 4, 24, 16. No, so these don't factor with these guys. This is good right here. If you could factor, if you knew rational root theorem, I'd ask you to factor that, but we're good. Okay, final one, number 4. Here's where we have an example where there are fractions and you're dividing the fractions. First thing I'd like you to do here is to write this linearly. In other words, write 2 over x divided by, and here's 1 over 1 minus y, or 1 minus 1 over y. The importance of that is because now you know you can multiply by this guy's reciprocal. Now you can't do a reciprocal until you have a common denominator here. So 1 needs to be divided by y somehow. So I'm going to multiply 1 by y over y, and I'm going to get, here's 2 over x divided by, now I have y minus 1 all over y. Notice how y is now a common denominator. Here's y minus 1. Now that I have that scenario, I can do 2 over x times y over y minus 1, multiply by the reciprocal, and multiply straight across. So we get 2y over x times y minus 1. By the way, I did not do the restrictions on this one. I'm sorry. X cannot equal plus or minus 2. On this one, the restrictions are kind of different because x and y are dependent on each other for this to make happen. The only thing I'd ask you to say here is that x times y minus 1 cannot be 0. If that's the case, in zero product property, that either means that x cannot equal 0 or y minus 1 cannot equal 0, which means x cannot equal 0 or y cannot equal 1. So there are the restrictions on that one. Remember, zero product property is different on that one than the other ones would do, like x plus y can't equal 0. These ones actually apparently aren't dependent on each other. See, if y equals 1, that becomes an issue. Same with x equals 0. Okay, final problems here. This one and then kind of a bigger one. Find the least common multiple to either create a common denominator or clear all fractions and then solve. So in other words, if I got a common denominator here, that would be awesome because if they're all dividing by the same thing and that side equals that side, then the top will be true. I'll explain that here. Take a look at all three of these guys and see what multiples of things they have. In other words, this has a multiple of x, this has a multiple of 3, this has 2 multiples of x. So the first guy is missing a multiple of x and a multiple of 3 in order to be the same as the others. This is missing 2 multiples of x, and this is missing a multiple of 3. If I write this as that to get common denominators on top and bottom, then I can work with that. 3x over 3x is 1, x squared over x squared is 1, 3 over 3 is 1. So I didn't change any of these values, but I will change the way they look. 3x times 1 is 3x over 3x squared. X squared times 1 is x squared. That's over 3x squared. And 3 times 6 is 18. That's over 3x squared. Once you're at this step, if they're all being divided by the same thing, then that just means that the top is true as is. If 3x over 3x squared plus x squared over 3x squared plus 18 over 3x squared, then 3x plus x squared equals 18. It's the same as leaving those guys out, or in other words, multiplying both sides by 3x squared. So if you did that from the onset, if you looked at that and said, oh, I know that that's my least common multiple, to clear all fractions, I could multiply both sides by 3x squared from the onset. You're still going to have to divide some stuff out. You're going to get to this step anyway. A lot of different ways you can look at this problem. Anyway, let's go ahead and solve for x. Going to subtract 18. And I'm going to get x plus 6 times x minus 3 equals 0. So x can equal negative 6 or 3. I want you to double check and make sure that both of these solutions work and that you don't end up dividing by 0 somewhere. We don't. If you plug in negative 6 or 3, we're good to go. So this one is good. The last problem, this one kind of hits it all at once. Got to find a common denominator. So first thing I'm going to do is start by factoring. This guy becomes x. Well, let's see what it becomes. I don't want to erase it before looking. This is x minus 3 times x minus 4. So it looks like if only we made this one x minus 3, wouldn't that be something special? So we can. If we factor out a negative 1 from here, better yet, if we multiply top and bottom by negative 1 over negative 1, then the, you know what, here, let's just rewrite this. 5 over x minus 3 times x minus 4. If we multiply top and bottom by negative 1 over negative 1, then we'll get minus negative 2 over x minus 3. And this one equals 5 over x minus 4. Okay. Looks like this one's missing a multiple of x minus 4. So let's get that multiplied there. And this one's missing a multiple of x minus 3. So let's multiply that there. Once you have that, you know, remember the second step that I wrote, over 3x squared over 3x squared? You don't have to do that anymore in this scenario. Remember, because this is an equation, we're not dealing with that stuff anymore. I'm just going to be looking at the top now. I'm going to completely ignore this now that we have lined up everything as we need to. So I have 5 minus negative 2 times x minus 4 equals 5x minus 15. So 5, what is that, plus 2x plus, oh no, minus, that's going to be a minus 8. Minus negative 2 times negative 4 equals 5x minus 15. And so 2x minus 3 equals 5x minus 15. Okay, keep going. 3x equals 12. And x equals 4. Make sure that that works in your final equation. You substitute 4 into here, and you can't substitute 4 in because 4 minus 4 is 0. That's no good. So, if x equals 4 is your only solution, guess what? It doesn't work. If that solution doesn't work, and if that's your only one, your answer is no solution. In other words, there is no value you could plug in to make this whole statement true here. So, doing the math, though, is still important. You have to know all the stuff to do that. And if x equals 4 worked, then that's your final answer. But that's it, and that's all. And that's all I got for you. I wanted to try and get through quickly. Hopefully I did. Chapter 9 quiz will be on Tuesday, February 24th. Any other questions, please ask me. Remember, I'm not around after school. That's why I want this video to be helpful for you. I will be around Tuesday during lunch, I sure hope. I'll let you know if I'm not. And please, best of luck to you on your quiz.